learning from life, how biodiversity can transform industries, cities, and society. For roughly 2 centuries, industrial civilization has run on a simple premise: take raw materials, apply energy and machinery, and produce goods, while treating waste, pollution, and ecological damage as externalities to be managed later, if at all. This model built extraordinary prosperity, but it also depends on linear extraction in a world that is, at every scale, cyclical. Nature does not produce landfills. A forest generates immense complexity in output: timber, food, clean water, stable climate, soil, medicine, while running entirely on sunlight and continuously recycling its own waste into new inputs. This is the foundation of an increasingly serious idea that biodiversity is not merely something to protect from industry, but a working model, and in many cases a literal substitute, for industry. Related movements make this concrete. Biomimicry copies biological designs, structures, and processes to solve engineering problems. Nature-based solutions go further, using living ecosystems themselves as functioning infrastructure: a wetland as a water treatment plant, a mangrove forest as a seawall, a fungal network as a waste processor. Together, they offer a genuine, if partial, alternative to how we build, manufacture, feed, heal, and govern ourselves. This essay examines that potential sector by sector, then turns to the harder question, where the analogy breaks down, and what it would actually take to scale these ideas into the backbone of a functioning economy, rather than a boutique alternative to one. Energy and materials, building like organisms build. Industrial materials science has historically solved problems with brute force: more heat, more pressure, more energy-intensive chemistry. Biological materials solve the same problems with information, precise molecular architecture assembled at room temperature, using minimal energy, from abundant elements like carbon, calcium, and silica. Spider silk, for instance, is pound for pound stronger than steel and more elastic than nylon, spun by an organism using no furnace and no fossil fuel input. Researchers have spent decades reverse engineering its protein structure to create synthetic analogs for use in body armor, medical sutures, and lightweight composites, potentially displacing petroleum-based fibers in specific applications. Mycelium, the root-like network of fungi, can be grown into rigid, fire-resistant, fully compostable material used for packaging, insulation panels, and even furniture, offering a real substitute for polystyrene and certain plastics in packaging and construction. Termite mounds offer a different lesson: not a material, but a system. Fungus farming termites in sub-Saharan Africa build mounds with passive ventilation shafts that maintain nearly constant internal temperature, despite extreme swings outside. Architects have directly copied this principle, most famously in Zimbabwe's Eastgate Center, a building cooled almost entirely through termite-inspired passive airflow, using a fraction of the energy of conventional air conditioning. This is biomimicry not as ornament, but as an engineering strategy that displaces mechanical HVAC systems altogether. Water and waste, ecosystems as infrastructure. Perhaps the clearest case for full substitution, not just inspiration, is in water treatment and waste processing, where biodiversity can often outperform industrial infrastructure on cost, resilience, and side benefits. Constructed wetlands, engineered to mimic natural marshes, filter pollutants and pathogens from wastewater using plants, soil microbes, and slow-moving water, often as effectively as conventional treatment plants for a fraction of the capital cost, with the added benefit of creating wildlife habitat rather than an industrial eyesore. New York City famously chose to protect and restore the Catskill and Delaware watersheds, paying farmers and landowners to maintain forest cover and reduce runoff, rather than build a new filtration plant that would have cost several $billion. The forest ecosystem, left intact, performed the filtration function for free. Coastal cities are experimenting with similar logic underwater. Oyster and bivalve reefs filter enormous volumes of water. A single adult oyster can filter dozens of gallons a day, while also acting as natural breakwaters that reduce storm surge, a role increasingly assigned to expensive engineered seawalls. On the waste side, black soldier fly larvae can consume food waste at industrial scale and convert it into protein-rich animal feed and fertilizer, offering a biological alternative to landfilling in parts of the conventional rendering industry. Agriculture, diversity as infrastructure, not ornament. Modern agriculture is arguably the sector most damaged by ignoring biodiversity, and the one where reintroducing it offers the most immediate leverage. Monoculture farming strips out the ecological relationships, predator insects, mycorrhizal fungi, pollinators, soil microbiota, that historically did pest control, nutrient cycling, and soil building for free, then replaces them with synthetic fertilizer, pesticide, and fossil fuel-intensive machinery. Agroforestry and polyculture systems, which interplant trees, shrubs, and crops in structured combinations, restore many of these functions. Beneficial insects suppress pests, root diversity improves soil structure, and mycorrhizal fungal networks improve nutrient and water uptake, reducing fertilizer dependency. Hedgerows and uncultivated field margins, once considered wasted land, function as habitat corridors that sustain the pollinators and pest predators the surrounding cropland depends on. None of this is a nostalgic return to pre-industrial farming, it is a reallocation of ecological labor that industrial chemistry currently performs badly and expensively. Cities, living systems as public infrastructure. Urban environments are usually seen as the opposite of biodiversity, concrete replacing habitat, but cities are increasingly integrating living systems as functional infrastructure rather than decoration. Urban tree canopy cools neighborhoods by several degrees through evapotranspiration and shade, directly reducing electricity demand for air conditioning, a nature-based substitute for mechanical cooling at the district scale. Green roofs and vertical gardens manage stormwater runoff that would otherwise overload sewer systems, while improving building insulation. Wildlife corridors threaded through parks and transit corridors allow species movement through fragmented urban land, simultaneously improving resident mental health and property values, effects now well documented in urban planning research. Structurally, biomimicry continues to inform how buildings and bridges are engineered. The internal lattice of bird bones and the logarithmic spirals of shells have informed lightweight, materially efficient load-bearing structures that use less steel and concrete for the same strength, a direct, if less visible, industrial substitution. Medicine and biotechnology. The pharmaceutical industry is, historically, a biodiversity mining operation. A large share of currently used drugs, from aspirin's willow bark origins to modern cancer treatments derived from marine organisms, trace back to compounds first evolved by other species as chemical defenses. Every species lost to extinction is, in a very literal sense, an unread page in a library of potential medicines. Protecting biodiversity is therefore not only an ecological argument but an economic and public health one. It protects the raw material of future drug discovery in a way no laboratory can independently replicate, because evolution has run trillions of chemical experiments that no synthetic chemistry program could afford to replicate from scratch. Beyond pharmacology, biomimetic engineering has produced surgical adhesives inspired by gecko footpads and antibacterial surfaces inspired by shark skin's microscopic texture, both offering alternatives to chemical antimicrobial coatings. Economy and governance, valuing what was never priced. None of the above scales without a shift in how societies value ecological function economically. The most important innovation here may not be biological at all, but financial, payment for ecosystem services, in which a city, company, or government pays directly to protect or restore an ecosystem because doing so is cheaper than building the industrial equivalent, as with New York's watershed program above. Emerging biodiversity credit markets attempt to extend this logic further, alongside carbon credits, to put a price on intact habitat itself. Though these markets remain immature and are still working out how to measure and verify what they're actually paying for, the limits of the analogy, it would be dishonest to present this as a frictionless replacement for industrial civilization, and a few real constraints deserve emphasis. Scale and speed. Biological systems are generally slower to establish and harder to standardize than industrial ones. A constructed wetland takes years to mature, a chemical treatment plant can be built and running in months. Ecosystem-based approaches are often better suited to supplementing industrial infrastructure than replacing it outright, particularly where a city's population already exceeds what surrounding natural systems could realistically process. Land use trade-offs. Nature-based solutions are often land-hungry relative to their industrial equivalents. A wetland performing the same filtration as a compact treatment plant requires far more physical space, a real constraint in dense urban areas where land is the scarcest resource of all. Energy density. Biomimicry has made real inroads in passive cooling, materials, and low-power systems, but no biological process yet approaches the energy density of fossil fuels or nuclear power. For heavy industry, large-scale manufacturing, and grid-scale power, biological substitution remains limited to component technologies, biofuels, bio-based feedstocks, rather than a wholesale alternative to industrial energy systems. Governance and maintenance. Living infrastructure requires long-term ecological stewardship, not a one-time capital investment, a governance challenge as much as a design one. Since budgets and institutions built around fixed infrastructure often struggle to fund ongoing ecological management, verification and measurement, biodiversity credit markets and ecosystem service valuations are still developing reliable ways to measure what they claim to sell, and remain vulnerable to the same greenwashing risks that have complicated carbon markets. The most credible version of this vision is not a wholesale replacement of industrial civilization with a return to wilderness, but a deliberate, sector-by-sector hybridization, treating biodiversity as a design library and, in specific contexts, as literal infrastructure, rather than as scenery to be protected at the margins of an otherwise unchanged industrial system. Watershed protection instead of new filtration plants where the land allows it. Mycelium packaging instead of styrofoam where performance allows it. Termite-inspired ventilation instead of mechanical cooling where climate allows it. Each of these is a real, working substitution today, not a speculative future technology. The deeper shift required is conceptual, recognizing that biodiversity is not a cost center competing with development, but a 4 billion-year-old research and development program whose solutions are frequently more efficient, more resilient, and less wasteful than what human industry has built independently. Protecting and integrating it is not an act of environmental charity, it is, in a very direct sense, good engineering. How can we use biodiversity to replace industries, improve cities and society globally in every way possible? Biodiversity can become more than something to protect. It can also serve as a model for designing industries, cities, agriculture, infrastructure, and economies that function more like healthy ecosystems. While biodiversity cannot literally replace every industry, it can inspire and support regenerative systems that reduce waste, restore ecosystems, and provide many of the goods and services society needs. The field of biomimicry, ecological engineering, and regenerative design already explores many of these approaches. Biodiversity is the foundation of a regenerative economy. Healthy ecosystems continuously recycle nutrients, capture carbon, purify water, regulate climate, and support countless species without creating persistent waste. Human industries can increasingly imitate these characteristics. Instead of a linear economy that extracts resources, manufactures products, and produces waste, societies can build circular systems where one process becomes the input for another. Examples include agricultural waste becoming building materials, food waste becoming compost or biogas, carbon dioxide becoming feedstock for chemicals and fuels, wastewater becoming irrigation water, organic waste supporting mushroom cultivation, industrial heat warming greenhouses. Nature demonstrates that waste can become a resource. Biodiversity-based agriculture. Agriculture can become increasingly similar to natural ecosystems. Instead of vast monocultures, farms can include food forests, agroforestry, silvopasture, wetland agriculture, mixed crop systems, pollinator habitats, native vegetation corridors, regenerative grazing where appropriate. Benefits include higher soil fertility, greater biodiversity, improved drought resilience, reduced erosion, lower fertilizer requirements, natural pest regulation, better water retention, long-term productivity. These systems often rely less on synthetic inputs while supporting wildlife. Production forests. Many industrial materials can come from sustainably managed forests. Examples include timber, bamboo, cork, natural rubber, plant fibers, medicinal compounds, essential oils, natural dyes, mushrooms, fruits, nuts, plant oils, resins. When managed carefully, diverse production forests can provide economic value while maintaining habitat, though they do not replace the ecological functions of old-growth forests. Biomimetic manufacturing. Nature manufactures materials using relatively low temperatures and pressures. Scientists are developing materials inspired by spider silk, seashells, bone, coral, wood, bamboo, mycelium, cellulose. Potential applications include biodegradable packaging, lightweight composites, building materials, medical implants, textiles, protective coatings. These approaches can reduce energy use and waste compared with some conventional manufacturing. Mycelium industries. Fungi can contribute to packaging, insulation, leather alternatives, bioremediation, soil restoration, composting, waste decomposition, water filtration, carbon storage in soils. Mycelium materials can substitute for some petroleum-based products in suitable applications. Nature-based construction. Buildings can incorporate biodiversity through green roofs, living walls, urban forests, rain gardens, wetlands, natural ventilation, daylighting, locally appropriate natural materials. Cities that integrate vegetation often experience cooler temperatures, improved stormwater management, and habitat for wildlife. Biodiversity-based water systems. Natural ecosystems can improve water management through wetlands filtering pollutants, forests protecting watersheds, floodplains storing floodwaters, riparian vegetation reducing erosion, mangroves buffering coastlines, healthy soils increasing water infiltration. These nature-based solutions often complement engineered infrastructure. Pollinator economies. Pollinators such as bees, butterflies, birds, bats, and other insects support the reproduction of many flowering plants and contribute to agricultural productivity. Communities can expand pollinator habitat by creating flower-rich parks, roadside meadows, native gardens, green roofs, hedgerows, pollinator corridors. This benefits biodiversity while supporting food production. Urban biodiversity. Cities can become networks of ecosystems. Possible features include urban forests, wildlife corridors, green roofs, pocket parks, community gardens, restored rivers, native landscaping, constructed wetlands, tree-lined streets. Benefits include cleaner air, cooler neighborhoods, reduced flooding, improved mental health, recreation opportunities, increased biodiversity. 7. Biodiversity-inspired energy systems. Natural ecosystems inspire decentralized energy systems. Examples include agrivoltaics combining crops and solar panels, floating solar integrated with reservoirs, algae cultivation coupled with wastewater treatment, biomass from agricultural residues, microgrids adapted to local conditions. These approaches can complement renewable energy sources while reducing environmental impacts. Circular materials. Nature continuously recycles materials. Human systems can increasingly use compostable materials, recyclable metals, reusable packaging, plant fibers, algae-based plastics, mycelium products, cellulose materials, recycled minerals. The aim is to minimize waste and keep materials in circulation. Biodiversity-based medicine. Many medicines originate from natural organisms. Conserving biodiversity increases opportunities to discover new antibiotics, anti-cancer compounds, antiviral agents, anti-inflammatory molecules, novel enzymes, biomaterials. Protecting ecosystems also preserves genetic diversity that may be valuable for future research. Ecological waste management. Decomposition processes can inspire waste systems. Organic waste can support compost production, vermiculture, mushroom cultivation, biogas generation, soil restoration. These processes return nutrients to ecosystems rather than sending organic material to landfills. Biodiversity-based transportation. Transportation infrastructure can better coexist with ecosystems by incorporating wildlife crossings, green bridges, tree-lined streets, rain gardens, permeable pavements, vegetated noise barriers. These measures reduce habitat fragmentation and improve urban environmental quality. Biodiversity and education. Education can increasingly include school gardens, outdoor classrooms, ecological restoration projects, citizen science, urban forestry programs, native plant cultivation, composting, ecological monitoring. Hands-on learning builds understanding of ecological systems. Biodiversity in the economy. Many sectors already depend on biodiversity, including agriculture, forestry, fisheries, tourism, pharmaceuticals, biotechnology, construction, landscape restoration, ecosystem management. Investing in healthy ecosystems can reduce long-term risks associated with degraded soils, water shortages, and climate impacts. Biodiversity-based cities of the future. 7. A future biodiversity-rich city could integrate extensive tree canopies, food forests in parks and neighborhoods, native plant habitats throughout the city, green roofs and living walls, wetlands for water purification and flood control, renewable energy integrated with green infrastructure, circular resource systems that reuse water and materials, walkable neighborhoods connected by parks and ecological corridors, buildings designed for energy efficiency and habitat creation, community spaces that support local food production and environmental education. Such cities aim to improve resilience, public health, and environmental quality while reducing pressure on surrounding ecosystems. A realistic global vision. Biodiversity is unlikely to replace all conventional industries, but it can transform how they operate. By drawing on ecological principles, societies can redesign agriculture, manufacturing, construction, water management, waste systems, and urban planning to become more regenerative. Combined with renewable energy, efficient technologies, circular material use, and sound environmental governance, biodiversity-centered design offers a practical pathway towards cities and economies that are more resilient, resource-efficient, and supportive of both human well-being and the natural world. Biodiversity-based agriculture. Biodiversity-based agriculture uses the natural interactions between plants, animals, fungi, insects, and microorganisms to produce food while improving the environment. Instead of planting a single crop over large areas, farmers grow diverse species that support one another. Trees provide shade and wind protection, deep-rooted plants bring nutrients to the surface, legumes naturally add nitrogen to the soil, and flowering plants attract pollinators and beneficial insects. Healthy soils rich in fungi, bacteria, and earthworms recycle nutrients and improve water retention, reducing the need for synthetic fertilizers and pesticides. Over time, these farming systems can become more resilient to droughts, pests, and climate variability while producing a wider variety of foods and supporting wildlife. Production forests. Production forests are forests that are managed to provide renewable resources while maintaining healthy ecosystems. Unlike clear-cut plantations that often grow only one species, diverse production forests contain many types of trees, shrubs, vines, mushrooms, and understory plants. These forests can produce timber, bamboo, fruits, nuts, medicinal plants, essential oils, fibers, natural rubber, resins, honey, and mushrooms over many decades. The trees continuously capture carbon dioxide, protect soils from erosion, regulate local climates, and provide habitat for birds, insects, mammals, and other wildlife. By harvesting resources selectively and allowing forests to regenerate naturally, production forests can provide long-term economic value while conserving biodiversity. Biomimetic manufacturing. Biomimetic manufacturing studies how nature creates materials and uses those principles to improve industrial production. Organisms such as spiders, mollusks, trees, corals, and fungi produce remarkably strong and lightweight structures using renewable materials and relatively low energy. Engineers can imitate these designs to create stronger composites, biodegradable plastics, efficient packaging, self-healing materials, water-repellent surfaces, and lightweight construction materials. Manufacturing inspired by biological processes often aims to reduce waste, lower energy consumption, use renewable feedstocks, and create products that can be safely recycled or biodegraded at the end of their useful lives. Mycelium and microorganisms. Fungi and microorganisms perform many essential ecological functions by decomposing organic matter, recycling nutrients, and supporting plant growth. Mycelium, the network of fungal threads beneath the soil, connects plants and helps transport water and nutrients in many ecosystems. Researchers are developing mycelium-based materials for biodegradable packaging, insulation, furniture, and construction components because the fungal fibers naturally bind agricultural waste into lightweight, durable structures. Beneficial bacteria and fungi also improve soil fertility, clean contaminated land and water through bioremediation, assist wastewater treatment, and help convert organic waste into compost or renewable energy. Harnessing these natural processes can reduce pollution and support more circular production systems. Nature-based construction. Nature-based construction integrates ecological principles into buildings and urban infrastructure. Architects can use renewable materials such as sustainably harvested wood, bamboo, hemp, cork, and other plant-based materials to reduce greenhouse gas emissions associated with construction. Green roofs, living walls, urban forests, rain gardens, and constructed wetlands help cool buildings, absorb rainwater, improve air quality, reduce noise, and provide habitat for wildlife. Buildings can also be designed to maximize natural lighting and ventilation, reducing energy consumption while creating healthier indoor environments. By treating buildings as part of local ecosystems, cities can become more comfortable, energy efficient, and environmentally beneficial. Biodiversity-based water systems. Healthy ecosystems naturally regulate the movement and quality of water. Forests intercept rainfall, slow runoff, increase groundwater recharge, and reduce soil erosion. Wetlands filter sediments, nutrients, and pollutants before water reaches rivers and lakes, while floodplains temporarily store excess water during heavy rainfall and reduce downstream flooding. Riparian vegetation along rivers stabilizes stream banks, shades waterways, and supports aquatic biodiversity. Protecting and restoring these ecosystems helps communities secure reliable water supplies, improve water quality, reduce treatment costs, and increase resilience to both floods and droughts. Pollinators and food production. Pollinators are essential components of many natural ecosystems and agricultural systems. Bees, butterflies, moths, flies, beetles, birds, and bats transfer pollen between flowers, allowing many plants to produce fruits, vegetables, seeds, and nuts. Conserving pollinator habitats by planting native flowering species, reducing pesticide use, preserving nesting sites, and connecting habitats through ecological corridors helps maintain healthy pollinator populations. Diverse pollinator communities increase the stability and productivity of food systems, while also supporting wild plant reproduction and broader ecosystem health. Biodiversity in cities. Urban biodiversity transforms cities into healthier environments for both people and wildlife. Street trees, parks, community gardens, restored streams, wetlands, green roofs, and native plant landscapes provide habitats for birds, insects, and other organisms while improving urban living conditions. Vegetation reduces the urban heat island effects by providing shade and cooling through evaporation, improves air quality by filtering pollutants, absorbs storm water during heavy rainfall, and offers recreational opportunities that benefit physical and mental health. Connected green corridors also allow wildlife to move safely through urban landscapes, increasing ecological resilience. Renewable energy integrated with biodiversity. Renewable energy systems can be designed to work alongside healthy ecosystems rather than replacing them. Agrivoltaic systems allow crops and solar panels to share the same land, reducing water loss while generating electricity and producing food. Floating solar panels on reservoirs can reduce water evaporation while producing renewable energy, provided they are designed to minimize ecological impacts. Biomass energy can utilize agricultural residues, forestry byproducts, or organic waste instead of requiring dedicated monoculture plantations. Careful planning of wind farms, hydropower, and transmission infrastructure can reduce impacts on birds, bats, fish, and sensitive habitats. Circular materials and waste reduction. Natural ecosystems continuously recycle nutrients through decomposition, allowing resources to remain in circulation. Human industries can adopt similar circular principles by designing products that are durable, repairable, reusable, recyclable, and biodegradable. Organic waste can be composted to improve soils or converted into biogas through anaerobic digestion. Recycled metals, glass, paper, plastics, and construction materials reduce the need for new resource extraction while lowering pollution and energy use. Circular production systems help conserve natural resources and reduce environmental impacts throughout product life cycles. Biodiversity and medicine. Nature contains an enormous diversity of organisms that produce unique chemical compounds for defense, communication, and survival. Many important medicines have originated from plants, fungi, bacteria, and marine organisms, and continued research may reveal additional treatments for diseases. Conserving biodiversity preserves genetic resources that could contribute to future medical discoveries, agricultural improvements, and biotechnology. Healthy ecosystems also help regulate disease transmission by supporting balanced ecological relationships among species. Ecological waste management. Ecological waste management treats waste as a resource that can be returned safely to natural cycles. Composting transforms food scraps and plant materials into nutrient-rich soil amendments that improve agricultural productivity. Earthworms accelerate decomposition through vermiculture, while fungi break down complex organic materials into simpler nutrients. Anaerobic digestion converts organic waste into renewable biogas and nutrient-rich digestate that can be used as fertilizer. These approaches reduce landfill use, lower greenhouse gas emissions, and return valuable nutrients to productive ecosystems. Transportation and green infrastructure. Transportation systems can better integrate with nature by reducing habitat fragmentation and improving environmental quality. Wildlife overpasses, underpasses, and ecological corridors allow animals to cross roads safely and maintain healthy populations. Tree-lined streets provide shade, improve air quality, and reduce urban temperatures, while permeable pavements allow rainwater to infiltrate into the soil instead of creating runoff. Vegetated roadsides, bioswales, and rain gardens capture storm water, reduce flooding, and provide habitat for pollinators and other wildlife. These designs create transportation networks that serve both people and ecosystems. Biodiversity education. Education is essential for helping societies understand the value of biodiversity and how ecosystems function. Schools, universities, botanical gardens, museums, and community organizations can teach ecological principles through outdoor learning, school gardens, habitat restoration projects, and citizen science programs. Students learn how soil organisms, plants, insects, fungi, wildlife, and climate interact within ecosystems. Environmental education also encourages sustainable lifestyles, responsible resource management, and participation in conservation and restoration efforts. Biodiversity and the economy. Healthy ecosystems support many sectors of the global economy by providing food, clean water, raw materials, pollination, climate regulation, and recreational opportunities. Investments in ecological restoration, sustainable forestry, regenerative agriculture, conservation, renewable materials, and ecosystem monitoring can create jobs while improving environmental conditions. Businesses that incorporate biodiversity into their operations may also become more resilient to resource shortages, climate risks, and environmental regulations. Recognizing ecosystem services and economic planning helps ensure that natural systems continue supporting human societies over the long term. Building a biodiversity-based society. A biodiversity-based society would seek to meet human needs while maintaining and restoring healthy ecosystems. Cities would integrate forests, wetlands, parks, green roofs, and community gardens into urban design. Agricultural landscapes would combine food production with soil restoration, wildlife habitat, and efficient water management. Industries would increasingly rely on renewable biological materials, circular manufacturing, and waste recycling. Energy systems would prioritize renewable sources that are carefully planned to protect ecosystems. Education, economic incentives, and environmental policies would encourage conservation, restoration, and sustainable resource use. Although no single approach can solve every environmental or social challenge, integrating biodiversity into agriculture, cities, industries, infrastructure, and governance can make societies more resilient, productive, and capable of supporting both human well-being and the long-term health of Earth's ecosystems. How can we create a totally regenerative society with biodiversity and increase abundance of essentials, products and ecology for every living being? A totally regenerative society would aim not only to reduce environmental harm but also to restore ecosystems, increase biodiversity, and provide essential goods and services in ways that can be sustained over the long term. In practice, no society can eliminate all environmental impacts, but many systems can be redesigned so that they contribute positively to ecological health while meeting human needs. Regenerative ecosystems as the foundation. The foundation of a regenerative society would be healthy ecosystems. Forests, grasslands, wetlands, rivers, coral reefs, mangroves, and other habitats would be protected and restored because they provide clean water, fertile soils, climate regulation, pollination, and countless other ecosystem services. Instead of viewing nature as separate from civilization, society would treat healthy ecosystems as essential infrastructure that supports life. Large-scale ecological restoration would reconnect fragmented habitats through wildlife corridors, restore degraded land, improve rivers and wetlands, and increase native biodiversity. These efforts would help stabilize ecosystems, improve resilience to climate change, and support a wide range of species. Food production that enriches nature. Agriculture would shift toward regenerative practices such as agroforestry, food forests, crop rotations, cover crops, integrated pest management, and careful soil stewardship. Farms would include diverse crops, trees, flowering plants, and habitat for pollinators and beneficial wildlife. Healthy soils rich in microorganisms would recycle nutrients and store carbon, reducing dependence on synthetic fertilizers while improving productivity and resilience. Food systems would also emphasize reducing waste, improving storage and distribution, and matching crops to local climates so that production becomes both efficient and environmentally responsible. Regenerative production forests. Managed forests could provide timber, bamboo, cork, medicinal plants, mushrooms, fruits, nuts, fibers, natural oils, and other renewable resources while maintaining ecological functions. Selective harvesting, mixed species planting, and natural regeneration would help ensure that forests continue to store carbon, protect biodiversity, regulate water, and provide habitat. These production forests would complement, not replace, protected old-growth forests and other high-value ecosystems that are best conserved primarily for biodiversity. Circular manufacturing. Manufacturing would increasingly use renewable and recycled materials while designing products for durability, repair, reuse, and recycling. Organic materials could be returned safely to natural cycles through composting or biodegradation, while metals, glass, and many other materials would circulate repeatedly through the economy. Industrial processes could also exchange resources so that the waste or excess heat from one facility becomes an input for another, reducing resource use and pollution. Living materials. Advances in biotechnology and material science can support the use of renewable biological materials such as sustainably sourced wood, plant fibers, mycelium, algae-derived products, and other bio-based materials. These materials can sometimes replace fossil-derived products while storing carbon or reducing pollution, provided they are produced within sustainable ecological limits. Biodiversity in cities. Cities can become ecosystems that support both people and wildlife. Urban forests, green roofs, community gardens, restored streams, native vegetation, wetlands, and parks provide habitat while improving air quality, reducing heat, managing stormwater, and enhancing quality of life. Compact, walkable neighborhoods connected by green corridors reduce land consumption and make it easier for wildlife and people to move through the landscape. Water systems that restore landscapes. Water would be managed as part of healthy ecosystems rather than simply moved through engineered infrastructure. Forest restoration, wetland conservation, floodplain restoration, rainwater harvesting, efficient irrigation, and groundwater recharge would improve water security while supporting biodiversity. Healthy watersheds naturally filter water, reduce flooding, and provide reliable supplies for ecosystems, agriculture, and communities. Renewable energy integrated with nature. Energy systems would rely primarily on renewable sources such as solar, wind, geothermal, hydropower where appropriate, and sustainable bioenergy from residues. Careful siting and design would reduce impacts on wildlife and habitats. Combining renewable energy with ecological restoration, for example through agrivoltaics or solar installations on already developed land, can help meet energy needs while minimizing land use conflicts. Ecological waste systems. Organic waste would become compost, biogas, or soil amendments rather than landfill material. Wastewater would be treated and reused where appropriate, and nutrients would be recovered whenever possible. This approach reduces pollution while returning valuable materials to productive ecosystems. Pollinator and wildlife networks. Every landscape could include habitat for pollinators, birds, mammals, amphibians, reptiles, and other native species. Flowering plants, hedgerows, wetlands, forests, and ecological corridors would connect habitats across both rural and urban environments. Healthy biodiversity increases ecosystem resilience and supports food production, water quality, and natural pest regulation. Regenerative economy. Economic success would increasingly be measured by improvements in natural capital, ecosystem health, public well-being, and long-term resilience in addition to traditional measures of production. Businesses could be rewarded for restoring habitats, reducing pollution, conserving resources, and supporting local communities. Markets, public policies, and investment can encourage innovations that create environmental benefits while remaining economically viable. Education and stewardship. Education would help people understand ecological systems and how their choices affect the environment. Schools, universities, community organizations, and businesses could provide practical experience in gardening, ecological restoration, sustainable resource management, and environmental monitoring. A society with broad ecological literacy is better equipped to care for its natural resources over the long term, increasing abundance for people and nature. In a regenerative society, abundance would be created by increasing the productivity and resilience of ecosystems rather than by continually extracting more resources. Healthy soils produce more food, restored forests provide renewable materials and regulate water, thriving wetlands improve water quality, and biodiverse landscapes support pollinators and wildlife. For people, this can mean more reliable access to clean water, nutritious food, renewable materials, cleaner air, stable energy, and healthier living environments. For other living beings, it means larger and better connected habitats, healthier ecosystems, greater genetic diversity, and improved opportunities to thrive. The overall objective is not unlimited consumption but lasting abundance within ecological limits. By allowing ecosystems to regenerate while using resources efficiently and responsibly, society can increase prosperity, strengthen resilience to environmental change, and improve the well-being of both humans and the millions of other species that share the planet. Achieving a regenerative society requires coordinated changes across ecology, technology, economics, education, and governance. There is no single solution, but many complementary actions can reinforce one another. Below is a more detailed explanation of how each part could be achieved. Restoring healthy ecosystems. The first step is to protect existing high-quality ecosystems because intact forests, wetlands, grasslands, coral reefs, and other habitats provide services that are difficult or impossible to recreate quickly. Strong conservation policies, sustainable land management, and enforcement against illegal exploitation can help preserve these areas. Degraded landscapes can then be restored by re-establishing native vegetation, improving soil health, reconnecting fragmented habitats through wildlife corridors, removing invasive species where appropriate, and restoring natural river and wetland functions. Restoration projects should use locally adapted native species and be monitored over time so that ecosystems develop naturally and remain resilient. Transforming agriculture. Agriculture can become regenerative by improving soil rather than simply extracting nutrients from it. Farmers can use crop rotations, cover crops, reduce tillage where appropriate, compost, mulches, and diversified planting systems to build soil organic matter. Trees can be integrated into farmland through agroforestry, providing shade, reducing erosion, storing carbon, and creating habitat for beneficial wildlife. Native flowering plants around fields support pollinators and natural predators of crop pests. Precision agriculture, soil testing, and efficient irrigation can help match inputs to actual needs, reducing waste while maintaining productivity. Food losses can also be reduced through better harvesting practices, storage, transportation, and distribution systems. Developing sustainable production forests. Production forests should be planned as diverse ecosystems rather than single-species plantations whenever feasible. Managers can combine multiple tree species with shrubs, understory plants, and fungi that complement one another. Harvesting should be selective and paced so forests continue to regenerate naturally. Long rotation periods, protection of old and large trees where appropriate, maintenance of deadwood for wildlife, and preservation of riparian buffers all help maintain biodiversity while providing renewable materials. Protected natural forests and sustainably managed production forests serve different purposes and should complement one another. Creating circular manufacturing. Manufacturers can redesign products so they last longer, are easier to repair, and can be disassembled for recycling. Standardized components, recyclable materials, and modular designs make it easier to recover valuable resources. Industrial facilities can exchange energy, water, and byproducts so that waste from one process becomes a resource for another. Renewable electricity, efficient machinery, and improved material recovery systems reduce resource consumption while lowering emissions. Businesses can also evaluate the environmental impacts of products throughout their entire life cycle and continually improve their designs. Expanding bio-based materials. Researchers and industries can develop renewable materials from sustainably managed biological resources such as wood, bamboo, agricultural fibers, algae, and mycelium. These materials should come from production systems that maintain soil health, biodiversity, and water resources rather than causing new environmental degradation. Investment in research, manufacturing capacity, and recycling infrastructure helps these materials become practical alternatives in applications where they perform well. Designing biodiverse cities. Urban planning can reserve space for parks, urban forests, wetlands, community gardens, green roofs, and native vegetation throughout neighborhoods rather than concentrating nature in only a few locations. Street trees reduce heat, improve air quality, and provide habitat. Restored streams and wetlands help manage storm water while supporting biodiversity. Mixed-use neighborhoods reduce transportation needs and make walking, cycling, and public transportation more practical. Planning green corridors between parks allows many species to move safely across urban landscapes. Managing water through natural systems. Watersheds should be protected by conserving forests, wetlands, and natural vegetation around rivers and lakes. Agricultural practices that improve soil health increase water infiltration and reduce runoff. Communities can install rain gardens, permeable pavements, green roofs, rainwater harvesting systems, and constructed wetlands to slow stormwater and improve water quality. Efficient irrigation technologies and water reuse systems help reduce unnecessary withdrawals from rivers and aquifers. Supporting pollinators and wildlife. Pollinator populations can be strengthened by planting diverse native flowering plants that bloom throughout the growing season. Reducing unnecessary pesticide use and protecting nesting habitats also supports pollinator health. Wildlife corridors, restored habitats, and careful land use planning reduce habitat fragmentation and can allow animals to move between populations, increasing genetic diversity and ecosystem resilience. Integrating renewable energy. Renewable energy projects should be located and designed to minimize ecological impacts. Previously developed land, rooftops, parking areas, and other disturbed sites can often host solar installations while reducing pressure on natural habitats. Agrivoltaics allow crops and solar panels to coexist in some settings, increasing land use efficiency. Wind, geothermal, hydroelectric, and other renewable systems should be planned with careful environmental assessments to reduce impacts on wildlife and ecosystems. Energy efficiency measures reduce overall demand, making renewable systems easier to implement. Building circular waste systems. Communities can separate organic waste from recyclable materials and non-recyclable waste at the source. Organic materials can be composted or processed through anaerobic digestion to produce soil amendments and renewable biogas. Recycling facilities should recover metals, glass, paper, and appropriate plastics efficiently. Manufacturers can participate by designing products that are easier to recycle and by using recycled materials in new products whenever feasible. Conserving biodiversity for medicine and biotechnology. Governments, universities, and research organizations can invest in biodiversity surveys, conservation programs, and ethical scientific research. Protected ecosystems preserve species that may contain valuable compounds for medicine, agriculture, or industry. International cooperation and fair benefit sharing arrangements can help ensure that discoveries based on biodiversity support both conservation and local communities. Building sustainable transportation. Cities can prioritize walking, cycling, and public transportation through well-designed infrastructure. Electric buses, trains, and other low-emission transportation reduce air pollution when powered by low-carbon electricity. Roads can include wildlife crossings, vegetated medians, and permeable surfaces where appropriate. Compact development reduces travel distances and preserves surrounding natural landscapes. Expanding ecological education. Education systems can include ecology, biodiversity, climate science, sustainable agriculture, and resource management throughout primary, secondary, and higher education. Students benefit from hands-on experiences such as school gardens, habitat restoration projects, field studies, and citizen science programs. Adult education, professional training, and public outreach help spread practical knowledge across society. Building a regenerative economy. Governments can encourage regenerative practices through incentives, research funding, environmental standards, and investments in restoration and sustainable infrastructure. Businesses can measure environmental performance alongside financial performance and adopt practices that reduce pollution and restore ecosystems. Financial institutions can increasingly support projects that improve ecosystem health while generating long-term economic value. Creating a culture of stewardship. Communities can participate in tree planting, habitat restoration, river cleanups, invasive species management, and monitoring local ecosystems. Indigenous knowledge, local experience, and scientific research can all contribute to better environmental management. When people understand that healthy ecosystems provide clean water, fertile soils, food, and climate stability, they are more likely to support long-term stewardship. Bringing the system together. A regenerative society emerges when these systems reinforce one another. Restored ecosystems improve water supplies and biodiversity. Healthy soils support productive agriculture. Sustainable forests provide renewable materials while storing carbon. Circular manufacturing reduces waste and resource extraction. Biodiverse cities improve public health and resilience. Renewable energy reduces greenhouse gas emissions, and education prepares future generations to maintain and improve these systems. Rather than maximizing short-term extraction, the central goal is to ensure that natural systems remain healthy and productive over the long term. By managing ecosystems responsibly, using resources efficiently, and continually restoring degraded environments, societies can increase the availability of food, clean water, renewable materials, ecological services, and economic opportunities while also improving conditions for the many other species that share the planet. Toward a regenerative society, biodiversity, abundance, and the redesign of everything. Sustainability, as a goal, has always had a modest ceiling: do less harm, slow the depletion, extend the runway. It is a subtraction problem. How much damage can be removed from an otherwise unchanged system? Regeneration asks a fundamentally different question. It asks how human activity could be designed so that the world is richer, ecologically, materially, socially. The longer that activity continues, the way a healthy old-growth forest holds more biomass, more species, more soil carbon, and more resilience than the sapling stand that preceded it decades earlier. A regenerative society is not one that merely survives within ecological limits. It is one whose economic activity actively expands those limits by rebuilding the living systems it depends on. This is a genuinely different design target than anything industrial civilization has built toward, and it requires rethinking materials, food, energy, cities, and, critically, the economic and legal systems that currently reward the opposite behavior. This essay lays out what that redesign looks like in practice, where real examples already exist at meaningful scale, and where the honest, unresolved difficulties remain. From linear to cyclical, the core design shift, industrial economies are built on a linear logic: extract raw material, manufacture, use, discard. Even at its most efficient, this model treats the earth as a warehouse and a landfill simultaneously, a stock to be drawn down and a sink to be filled up. Living systems operate on the opposite principle. A forest generates enormous output: timber, food, water filtration, climate regulation, medicine, using only sunlight as an energy input, because every material within it is designed to become the input for something else. A falling leaf is not waste, it is the next season's soil. Regenerative design tries to rebuild human economies on the same cyclical logic, formalized in what circular economy theorists call the distinction between biological nutrients and technical nutrients. Biological nutrients, food scraps, natural fibers, biodegradable packaging, are designed to safely return to the earth and rebuild soil. Technical nutrients, metals, certain plastics, electronics components, are designed to be endlessly disassembled and recirculated at the same quality, rather than downcycled into lower-grade material until they are eventually landfilled. Applied consistently, this reframes waste itself as a design failure rather than an unavoidable byproduct of production. Abundance as a compounding asset, not a fixed pool. The most counterintuitive part of regenerative thinking is its treatment of abundance. Conventional economics treats natural resources as a fixed or depleting stock to be rationed. Regenerative design treats healthy ecosystems as a compounding asset, one that, properly managed, produces more output next year than this year, the same way a well-tended orchard yields more fruit as the trees mature, not less. Soil is the clearest example. Conventional monoculture farming steadily depletes soil organic matter, requiring ever-increasing synthetic fertilizer inputs just to hold yields flat. Regenerative practices, cover cropping, no-till farming, diverse crop rotations, integrating grazing livestock in managed rotations, rebuild soil organic matter over time. Richer soil holds more water, buffers against drought, sequesters more carbon, and supports higher yields with fewer external inputs, all of which reinforce each other. The system gets more productive the longer it is farmed regeneratively, the inverse of the depletion curve that defines industrial agriculture. Polycultures extend this logic spatially. A monoculture field is optimized to extract one output: corn, soy, wheat, as efficiently as possible from a given acre, producing nothing else and requiring external inputs, pesticide, fertilizer, irrigation, to suppress the ecological complexity that would otherwise emerge. A food forest or agroforestry system, by contrast, stacks multiple yields on the same land: canopy fruit and nut trees, understory shrubs, ground-level vegetables, fungi, and habitat for pollinators and pest predators, all occupying different ecological niches simultaneously. The result is not a trade-off between yields but a multiplication of them: more total output per acre, distributed across many products rather than concentrated in one, with far less vulnerability to a single pest, disease, or price collapse wiping out the entire harvest. Ecological restoration operates the same way at landscape scale. Restoring a degraded watershed does not just protect nature in an abstract sense, it produces clean drinking water, flood buffering, fish populations, carbon storage, and recreational and tourism value, all from the same acreage, all increasing as the ecosystem matures. Restored mangrove forests simultaneously nurse commercial fish stocks, buffer coastlines against storm surge, and sequester carbon at rates several times higher than equivalent terrestrial forest, a single restoration investment generating multiple, compounding streams of value rather than a single extracted product. Distributed production is the final abundance lever, and it operates through resilience rather than yield. Centralized industrial systems create fragile abundance. A single factory, refinery, or shipping bottleneck failing can create shortages across an entire region, because the system has no redundancy. Distributed regenerative systems, local food networks, community-owned renewable microgrids, localized material recovery loops, trade some economies of scale for redundancy, so that abundance does not depend on any single point of failure. This is a different, and arguably more honest, definition of abundance: not maximum output under ideal conditions, but reliable sufficiency under real-world disruption. Domain-by-domain redesign. Food, regenerative agriculture and agroforestry replace monoculture as the default model, rebuilding soil and biodiversity with each growing cycle rather than depleting it. Urban agriculture and vertical farming shorten supply chains and reduce transport losses, bringing production closer to consumption. Fermentation-derived proteins and mycoprotein offer complete or near-complete nutrition using a small fraction of the land and water footprint of livestock, freeing land currently used for feed crops and grazing for restoration or diversified food production instead. Materials. Mycelium-based materials, algae-derived plastics, and other biologically grown materials offer biodegradable alternatives to petroleum-based plastics and foams across packaging, insulation, and even furniture. Urban mining, recovering metals and rare earth elements from discarded electronics, reduces the need for new extractive mining, treating existing cities as material reserves rather than only sources of waste. Energy, decentralized renewable energy, solar, wind, and increasingly agrivoltaics, where solar panels are installed over farmland that continues to produce crops or graze livestock beneath them, allows the same land to generate both food and power simultaneously, compounding output rather than forcing a choice between them. Water, watershed restoration and constructed wetlands function as primary water infrastructure rather than a backup to conventional treatment, as demonstrated by cities that have chosen to protect and restore upstream forest watersheds instead of building costly new filtration capacity. Rainwater harvesting integrated directly into building design further reduces dependence on centralized water systems. Cities, biophilic design, buildings and neighborhoods that actively host and are structured around living systems, including green facades, integrated wetlands, urban forest canopy, and wildlife corridors, shift cities from being net ecological extractors to potential net contributors to regional biodiversity and climate stability, while simultaneously improving air quality, temperature regulation, and resident well-being. The load-bearing wall, governance and economics. None of the above scales without a parallel redesign of the economic and legal systems that currently reward the opposite behavior, and this is the part most often left out of regenerative visions. True cost accounting. Conventional prices generally exclude the ecological cost of production, soil depletion, water pollution, carbon emissions, treating them as externalities borne by someone else. Later, regenerative practices, by contrast, often carry near-term costs, transition periods with lower yields, more labor-intensive management, without being credited for the long-term ecological value they create. True cost accounting, pricing goods to reflect their full ecological footprint, positive or negative, is necessary to make regenerative production economically competitive rather than a voluntary tax paid only by producers with a strong ethical commitment. Commons-based stewardship, land trusts, community land ownership, and cooperative resource management structures reward long-term ecological health over short-term extraction, because the people managing the resource are also the people who depend on its long-term productivity. Emerging biodiversity credit markets attempt to extend a similar logic into mainstream finance, financially rewarding landowners for verified ecosystem restoration alongside or instead of carbon credits, though these markets remain young and are still developing reliable measurement standards. Redefined metrics. Gross domestic product measures the volume of economic activity, not its ecological direction. A barrel of oil extracted in a wetland restored register identically as economic throughput, even though one depletes and the other compounds. Regenerative societies generally require parallel metrics, natural capital accounting, genuine progress indicators, ecological footprint tracking, to actually know whether a given policy or investment is building abundance or merely relocating scarcity. The honest tension, speed, scale, and the transition. Every element described above already exists and works at meaningful scale. Regenerative farms measurably outproducing depleted monoculture soils within a few growing seasons. Restored watersheds supplying major cities more cheaply than new treatment infrastructure. Mycelium packaging replacing plastic foam in real supply chains. The unresolved question is not whether regenerative systems work, but whether they can be scaled fast enough to meet the material needs of 8 to 10 billion people at the speed extraction currently does, without requiring a difficult transition period of reduced throughput in some sectors along the way. Serious regenerative economy frameworks. Kate Raworth Stone at Economics, which frames the goal as meeting human needs within planetary boundaries rather than maximizing growth. The Ellen MacArthur Foundation Circular Economy Research, Decades of Permaculture Design Theory, treat the scaling question as the defining design challenge of the coming decades, not a solved problem and not an impossibility. That is a more honest framing than either the utopian claim that regeneration can seamlessly replace extraction overnight, or the fatalist claim that it is a fringe idea incompatible with a global economy. The evidence suggests it is neither, a working set of principles and proven examples, whose central unfinished task is scaling the economic and governance systems around them fast enough to matter. A regenerative society is not a return to a pre-industrial past, nor a purely technological fix layered onto an unchanged economic logic. It is a redesign of the basic loops, material, agricultural, energy, urban, financial, so that human activity increases the complexity and productive capacity of the living systems it depends on, rather than steadily drawing them down. The biological and ecological tools to do this largely already exist and are proven at real scale. What remains unbuilt is the economic and governance architecture to make regenerative practice the default, competitive choice rather than the exception maintained by a minority of committed practitioners, which is less a scientific problem than a design and political one, and arguably the more difficult of the two.